So, hey, calculus class. Say hi to those of you that are in the room.
Hi. Hello.
Louder. I don't know if they can hear you.
Hi. Hello.
So there are some fellow students here. Today we're just going to finish 5.5, which was the last section before we get into, or before our exam. On Wednesday we will review, and on Thursday will be our Chapter 5 exam. So, important that we get some things cleared up and finished up today, and we'll start that right now. What I want you to do is go ahead and write this example. If you need to pause the video to do that, do that. So, an observer measures the outside temperature every hour from t equals 0, which is noon, to t equals 6, which is 6 o'clock. And it's as follows here in this table. At time 0, the temperature is 64. At time 1, we're at 65. 2, we are at 66. 3, we are at 68. 4, we are at 69. 5, 69. And 6, 70. So, while this data looks like it's, 6 or 7 separate points of data, it's actually a continuous change. Temperature changes continuously. So, the question we're being asked is to use a trapezoidal sum to find, or we could say approximate, but to find the average temperature over the 6-hour period. So, while these are data points similar to what you might look at right here, this temperature change is actually a continuous change and might look something like that. So in order to calculate an average temperature, we need to estimate what the average of all these infinite number of temperature readings would be, and we do that with a trapezoidal sum. So we're actually going to be estimating the area underneath all this, and then dividing by 6, which is the number of hours that these measurements are taking place. So if you just recall that the average value of a function would be, over the interval from a to b, The average value over a to b is 1 divided by b minus a. So when I mentioned dividing by 6, that's where this comes in, times the definite integral from a to b of whatever the function is that you're dealing with. Okay? But remember, all we have here is data points, which we then can make look like a continuous function. So a trapezoidal sum is actually going to be an approximation of this part of the integral. And so that is the sum of all these areas. And so we're actually going to set up the trapezoidal sum. Remember that it's the height divided by 2. So the height of all these trapezoids is going to be 1. It's the change in your x, or in this case your t value. So it's 1 divided by 2 times the first height plus 2 times the second height. And this is what we went over last time in class, plus 2 times the third height, and so on. So it's at this point that we just pull out a calculator and we actually just calculate this to see what this integral approximately is going to be using this trapezoidal sum. So as I'm sure you all just got done pausing the video and typing this in, calculating this, this is actually a total of 404. Okay? So this integral piece right here is going to be a sum of 404. And now when we divide by the interval distance, which is right here, we divide by 6. So the average temperature is going to be 404 divided by 6, which is 67.3 degrees repeating. That's going to be your average temperature over that interval. So now that we have this trapezoidal approximation, we're actually going to look at another rule. This rule is once in a while on the final exam, it's very similar to the trapezoidal rule. In fact, it uses the exact same idea as the trapezoidal rules. It's just a little bit different. So Simpson's rule. So we're going to say use Simpson's rule for the same set of data. Okay, this is Simpson's rule, where this capital S is approximately the integral from a to b of f of x dx. All right, and in the absence of an actual function that we can integrate, this is about as close, about as accurate as we can get, is using either Simpson's or the trapezoidal rule. All right, so this approximation, and we're going to use the same idea we did on Friday's notes with our bases and all those types of things. So this capital S is the height divided by 3. So same exact height of each subinterval. Times that first base, that base 0, base sub 0, plus 4 times the base of 1 plus 2 times the base of 2 plus 4 times the base of 3 plus 2 times the base of 4, and then that continues all the way out until you get the last base, which would be base of n. So it's the first, and then it goes 4, 2, 4, 2, and that pattern continues until you get to the very end. You would just multiply by 1. But this only works when the interval a to b is partitioned into an even number. Of n subintervals. So, using the same data, where these are our base lengths, so these fit right here for your bases. Try to calculate what Simpson's rule would have that integral as. So the approximate what this would be, and then we divide by 6 and we'll get our average again. So you should have fit our data into the algorithm like this. First base does not have a multiplier, and then everyone after that goes 4, 2, 4, 2, 4 until you get to the very last one. You'll always end in a 4 times this number, and then you'll add your last data point there. When you do that, you actually get, and multiply or divide by 3, you actually get the exact same thing we got on the trapezoidal rule. And then dividing by 6, you get your average time to 67.3. All right. The 5-5 assignment will be due Wednesday. It's numbers 2 through 5, 7 through 12, which 2 of those problems in there, 2 and 8, were hopefully done already today. And then 14 through 17. So, good luck. See you all at Math Support PLT, especially if you're watching this video, unless you are in class. Say hi again, everybody.
Hi.
Unless you're in class and you just miss the sound of my voice.